Let's go. Have you written down the question? So when you're given a question like this, there are certain steps to apply. So I'm going to make it very, very easy. First of all, take note of these numbers here. 6666. It means that the coordination number is 6, which means it's an octahedral complex. Abi? And then when you see CFT, it means the splitting of d orbitals. So d orbital splits 2 up, 3 down for octahedra. Are we together? It splits 2 up, 3 down for octahedra, while it splits 3 up, 2 down for tetrahedra. So this is for tetrahedra and this is for octahedra. Are we together? Just pay attention. Now for the octahedral complex, here is the x square to y square and the z square. Here is the xy, this is the xz and the yz. This up here is called the EG, this down is called the T2G. For tetrahedra, this is the dxy, the xz, the yz, the x square to y square and the z square. Here is called the T2, while this is called the E. They don't put G for tetrahedra, but you put the G for octahedra. Are we together? Are we together? Now, another thing that you must take note of is the ligands. Here you have Cn, here you have H2O, here you have Cl, and here you have PPH3. Now, I've told us that strong field ligands are ligands that have carbon, nitrogen, or phosphorus as their donor atom. These are strong ligands. Ligands that have carbon, nitrogen, or phosphorus as their donor atom are strong ligands. While weak ligands are ligands that does not have carbon, nitrogen, or phosphorus. For example, H2O is a weak ligand. There's no carbon or nitrogen or phosphorus there. Chlorine is a weak ligand. Basically, all halogens are weak ligands. Are you seeing that? All halogens. OH is a weak ligand. So anything that does not have carbon, nitrogen, or phosphorus as the donor atom is a weak ligand. Now, let's now come back to the splitting. You see this splitting? Whenever you have a strong ligand, this splitting will be large. Are we together? When you have a strong ligand, this splitting now will be as large as this. It will be as large as this. I'm just taking for example. Let me use octahedra now so that we can follow well. So this is also EG, this is T2G. Both of them are octahedra now. Are we together? Both of them are octahedra. But this one is a strong ligand. Meanwhile, this one is for a weak ligand. Please follow me. Both of them are octahedra. This is for a strong ligand. This is for a weak ligand. How do you know strong ligand? Ligand that have carbon, nitrogen, or phosphorus. How do you know weak ligand? Any other ligand that does not have carbon, nitrogen, or phosphorus. So when you have weak ligand, the splitting will be small like this. When you have strong ligand, the splitting will be large like this. Are we together? Now, if I say you have D6, for example, are we there? D6, and then you are looking at a strong ligand. If you have D6 and a strong ligand, this is how you fill your electrons. You know, one thing about electrons is that they require energy to pair up together. You know that, right? They require energy to pair up together. And for electron to also jump up, it will also require some amount of energy. So there are two energies we're looking at now. We're looking at pairing energy and splitting energy. What is pairing energy? Energy required for electrons to pair. Splitting energy, energy required for electrons to jump, that is to split. So let's work together. So if you have a D6, you know, naturally, this is how it would have been. Since this 5 orbitals, 1, 2, 3, 4, 5. You say 1, 2, 3, 4, 5, 6, right? Is that not it? So this one will work if we're not looking at the splitting of d orbitals. It would have worked perfectly. But now we're looking at the splitting of the d orbitals, so it will not work as we thought it would. So now let me show you what will work. So for a strong field, you still feel your electrons 1, 2, 3. Now the fourth electron should naturally come here. Are we together? It should naturally come here, but it would not. Why? Because the distance is too far. So the electron cannot jump here. What does that mean? It means that the energy that it will use to split is lesser than the energy that it will use to pair. So here you say splitting energy is lesser than pairing energy. Are we together? Here you say splitting energy is lesser than pairing energy. If splitting energy is lesser than, sorry, splitting energy is greater than pairing energy. Yes, the energy to use to jump is higher than the energy to use to pair. What I'm saying is that the electron cannot jump. Why? Because the energy to use to jump up is higher than the energy to use to pair up here. So what will you do? Is to just pair. Are you seeing that? So instead of the fourth electron should come here, it will continue from here. So 4, 5, and 6. Are we together? So you have 1, 2, 3, 4, 5, 6. This is for a strong field ligand. And why is that happening? Because the splitting energy is greater than the pairing energy. But for a weak ligand, let's look at a weak ligand. You want to feel this 6 again. You go 1, 2, 3. Now you might want to pair again, but it will not work. Why will it not work? Because the energy to use to pair is now greater than the energy to use to jump. So it will just rather jump up. So you now have 4, 5, 6. Are you seeing that? So looking at it now, this is a D6, this is a D6. This is a D6 with a strong ligand. This is a D6 with a weak ligand. Now let's now look at the magnetic property of both. Now, magnetism, that is, when you say magnetism, is divided into two. We have the para and we have the what? The di. We have paramagnetic and we have dimagnetic. Paramagnetic means when you have at least one unpaired electron. What does it mean? Meaning you have at least one electron that is not pairing. Are we together? One electron that is not paired. That is paramagnetic. But diamagnetic means all are paired. Diamagnetic means all of them are paired. No single one is unpaired. But para means at least one is unpaired. So if you look at it now, this guy, is it paramagnetic or diamagnetic? It is diamagnetic because all of them are paired. Meanwhile, this one is what? Paramagnetic because you have at least 4 unpaired electrons. So and even if it's 1, it is paramagnetic. But now there's now 4, so it is paramagnetic. Are we there? So we're about to solve these questions. Are we together? So if you want to write, let's write before we solve those questions. Say you see this one that is strong field. If you notice, the electrons are the electrons are pairing down here. This is regarded as a low spin complex. Now this one now, you see the electrons went up. This is regarded as a high spin complex. So this is a low spin complex and this is a high spin complex. Why is it a low spin complex? Because all the electrons are pairing down here. And why is this a high spin complex? Because electrons jump up there. So that you take note of that. So that's what I wanted to add. I'm going to take these questions, all these ones. So looking at this now, is this a weak ligand or a strong ligand? Is it weak or strong, Merit? This one, is it a weak or a strong ligand? It's weak because it does not have carbon, nitrogen, or phosphorus as a donor atom. This one, is it a weak or a strong one? Because phosphorus is a donor atom. Weak or strong? Weak. Chlorine. There's no carbon, nitrogen, or phosphorus here too, so it's weak. What about this one? Is it weak or strong? Strong because there's carbon and there's nitrogen. So good, let's go. So we're taking this one first. First step, since we are dealing with MnH2O6 2 plus, the first step is to find out if it's a weak or a strong free ligand. So you say H2O is a weak ligand. That's the first thing. We point that out. So now you know the splitting you are going to do is this one and not this one. All right, moving on. Next thing you want to do is to find out the metal center where it is in the periodic table. Mn is what in the periodic table? 25. You try and locate it. It's 25. Iron is 26. Although they will give you, but you just have to write it out and then write down the electronic configuration. Yes, they'll give you in the exam, but you would have to write out the electronic configuration by yourself. So Mn25, the electronic configuration will be argon 4s2 3d5. You can also write it as 3d5 4s2. Are we together? Anyone works, but me I like 4s2 3d5. This one too. Now the reason why I'm putting argon here is because argon is 18 in the periodic table. So it's a octet, like it has all its orbitals completely filled, and that's why it is 18. So instead of writing 1s2, 2s2, 2p6, 3s2, 3p6, this is argon. So instead of writing all of this, just write argon. That covers for 18. Then this one is now 19, 20, abi? Then plus 5, 25. So that covers for 25. So I've attended to that. So what you want to do next is find the oxidation state of manganese here. Are you seeing that? Oxidation state of manganese. It's usually very easy to calculate considering that H2O here is a neutral ligand. Are we together? H2O is a neutral ligand, meaning that H2O does not have a charge. So calculating it to be Mn plus 0 times 6 equals to what is outside here? 2. So Mn equals to plus 2. Are you seeing that? So Mn is plus 2. So if Mn is plus 2, and before we had argon 4s2 3d5, plus 2 means that it should lose 2 electrons. So Mn2 plus will now become argon 4s0 3d5. Why are we losing from here? Because this one is 4. Are we together? You lose from 4 before you lose from 3. Are we there? You lose from the 4 before you lose from the 3. If you have 5 and 4, you lose from the 5 before you lose from the 4. If you have 6 and 5, you lose from the 6 before you lose from the 5. The reason is because 4 is the outermost shell. Meanwhile, 3 is still inside. So 4 is the outermost shell. So you lose from 4 before you lose from 3. So that's why we have 4s0 3d5. So what we now know now is that what we are dealing with is a d5, not a d6. Are you seeing that? It's a d5. So how do we feed the electron? Knowing that it is a weak field ligand. We say 1, 2, 3. Are we going to pair? Are we going to pair? No, we don't pair. We split. So that's the answer. So look at the question. The question says that we should do what? Predict the magnetic property and the number of unpaired electrons. How many unpaired electrons is here? 5. Is it paramagnetic or diamagnetic? So you now say that it is paramagnetic with 5 unpaired electrons. I'm teaching you how to answer exam question. So you see how you see step where I follow. You see the steps I follow to get to this place now. Now your exam now, just rush and write nonsense. Then you now come and say you wrote to. You didn't write to, you wrote nonsense. I'm telling you now. Okay, let's take the next one. The next one is this guy, Abi. MnCN. Let's quickly take that one. Let me clean all of this. MnCN 6 4 minus. Are we here? MnCN 6 4 minus. Let's do this together. Once again, Cn is what? Weak or strong? So you say Cn is a strong ligand. So I've pointed that out. So Mn being a strong, Mn is now what now? Again, 25, abi? Which is still argon 4s2 3d5, abi? Okay. So what you want to do next is to calculate the what? Oxidation state. Cn has a charge of -1. Are we together? Cn has a charge of -1. So Mn plus -1 times 6 equals to what? -4. Are we seeing that? So Mn minus 6 equals -4. Collect like terms. Mn equals to -4 plus 6 equals to what? Plus 2. So Mn being plus 2, you now say Mn 2 plus will now be what? Argon 4s0 3d5. Again, right? So it's still a D5, but a strong ligand. So for affinity, what will we do? 1, 2, 3. Will I put it here? No. So 4 and 5. So now, how many unpaired electrons do we have? 1. Is it paramagnetic or diamagnetic? Paramagnetic. What should say? So this is what we'll have. So you have to solve the other two by yourself.